So I think what I'll do now is, without further ado, is I will introduce Sophie. So Dr. Sophie Parsons is a life cycle analysis specialist, now at the National Composite Centre, the NCC. I know Sophie fairly well from our roles as strategic advisors for the Institute of Materials, Minerals and Mining. I know that Sophie is going to talk a little bit about her sort of career up to this point. So I think rather than me waffling on, what I'll do is I will hand you over to Sophie. And so, Sophie, whenever you're ready, that will be great. And again, thank you very much for agreeing to do the talk.
Sure. Thanks very much, Simon. Right, I will share my screen. There we go. Hopefully you can all see that okay.
Yep, we can see that, Sophie.
Fab. Right. Okay. Well, thank you very much for coming along to listen to me talk this evening. So I'm Sophie. I've been working in sort of life cycle assessments now for over about 10 years or so. So I started out working for the National Physical Laboratory over in Teddington in the materials team there. And then I sort of spent some time in commercial consultancy and also then went into academia for a little bit of time. So I joined NCC back at the beginning of this year, but before then I was a lecturer in mechanical engineering at the University of Bath. So the fairly kind of constant part of my career over the past 10 years or so has been that kind of focus on new and emerging materials and technology, but I've worked across a real range of different areas, everything from kind of nanomaterials to new solar technology to even microbial alternatives to palm oil as well. So yeah, a real range of different things. But for me, why I find this area really interesting and exciting is that as we kind of transition towards a low carbon economy, what's really important as we start developing new technology to enable us to do that is to ensure that technology is actually sustainable. And that we're not just kind of burden shifting from one part of the life cycle to another, and in kind of focusing on reducing carbon, we're not forgetting about some of those other environmental impact categories. So whilst it's really important that we're kind of applying this systems thinking and sort of life cycle thinking, life cycle assessment is a really useful tool to enable us to do that. But there are some real sort of challenges of applying life cycle assessments to new and emerging technology and kind of new materials. There's lots of uncertainty there. We don't know what that technology is going to look like when it's commercialized. There's lots of issues around lack of data. There also might be some really interesting kind of material specific challenges that we have to deal with through life cycle assessment as well. So those sort of methodological challenges are what I find really exciting and really interesting, and I certainly hope that after this talk today you will also think that too. So without further ado, I will make a start. So brief outline for what I'm going to talk about today. So I'm going to just do a little bit of an introduction to NCC and some of the activities that we've got going on in sustainability. I'm going to talk a little bit about why measuring sustainability is increasingly important. I'm going to give a bit of background to life cycle assessment, applying life cycle assessment to new technology, and I'm going to give some new technology examples. So I'm going to draw on some of the work I've done previously with nanomaterials, and of course talk a little bit about some of the challenges applying life cycle assessments to composite materials as well. And then I'm going to finish off by talking a little bit about managing uncertainty as well. So for any of you who don't know who the National Composite Centre are, so we are one of 7 different catapult centres focused on high value manufacturing in the UK. Largely focused on kind of industrial research, work across a range of different sectors, everything from kind of construction through to energy, automotive, aerospace, defence, real kind of range of different areas. But for us, really kind of growing area over the past few years has been sustainability and has been kind of tackling kind of growth in sort of green economic growth. So this has been kind of driven from increased engagement around climate risk and better understanding of climate risk. It's been driven from increased sort of engagement with sort of sustainable development goals, and then also some kind of material specific challenges as well. So for example, around plastics and some of the kind of environmental aspects around plastics. So more sort of widely, where do kind of composites fit in within this? So from the feedstock side of things, 98% of our matrix materials typically derive from petroleum, and 95% of our fibres, again, derived from non-renewable resources. And then at the end of life side of things, very small amounts of composites are recovered at end of life. And even smaller amounts of composite is then reused in the secondary application. So we've got these kind of real challenges both at the kind of front end of the life cycle and also at end of life in terms of making composites more sustainable. So one of the initiatives that we've got going on at the moment is SOSCOM, which is partnership between NCC and CPI, so another one of our high value manufacturing catapults. And what we're looking at doing with CPI really is sort of supporting industry and academia in terms of tackling some of those kind of key challenges with sustainable composites uptake. So drawing from kind of CPI's background on the kind of raw materials and feedstock side of things, and our expertise in kind of manufacturing, to be able to kind of pool resources, enhance kind of capability, kind of bring together our networks in order to kind of accelerate take up of sustainable composites and kind of supply chain as well in the UK. So we've got a real range of different activities in sort of sustainability going on at NCC at the moment, ranging from activity looking at end of life through to developing new sustainable kind of products. We're doing lots of work on kind of bio-based composites as well, recycling technologies, looking at creating networks around improving kind of circularity in composite supply chain. I was doing a lot of work on analysis and end-to-end life cycle assessments, and then creating sort of demonstrators and things like that for end of life and secondary sort of materials also. So I will say, if you are a student listening to this and you're interested in materials and you're interested in sustainability, I would certainly look out for our kind of graduate scheme opportunities, because it's a real growing area for us at NCC. It's definitely one of the sort of fastest growing areas at NCC, and there's loads to get involved with on the sort of sustainable composite side of things. So that's a bit about sort of NCC. So more broadly, why are more people interested in measuring sustainability? So from kind of a sort of slightly more generic side of things, we might want to look at improving product design. We might want to look at supporting kind of internal sustainability efforts, so these kind of internal drivers. Increasingly, there's an interest in kind of corporate reporting and whether or not that's reporting to kind of external reporting mechanisms like CDP or GRI, but also within the supply chain as well. There's often pressure for companies to report to things like CDP supply chain, or to report into kind of supplier management software, which requires you to measure some of your environmental impacts. You also might want to be producing environmental product declarations, EPDs, or other types of environmental declarations. So these would be kind of your external drivers for measuring sustainability. So what's kind of popped up more recently, and what's been a kind of real accelerator in terms of driving engagement to measure sustainability, has been things like science-based targets. So science-based targets, and you can see from the graph on the right there, you've got this kind of the grey trajectory of kind of where we're going, and then the blue of kind of some of the current policies and current commitments that businesses have made. And you can see between the blue and the green and the yellow line, there is a bit of a gap there in terms of what companies have committed to, and actually what is going to allow us to meet that below 2 degrees or below 1.5 degrees rise in temperature. The idea of the Science-Based Targets Initiative is to ensure that actually companies, when they're setting targets, that they're setting targets which are consistent with commitments around no more than 2 degrees or no more than 1.5 degrees rise. You've got a huge increase in companies engaging with science-based targets, and now across a range of different sectors, everything from Tesco's to Kinetic, engaging with Science-Based Targets Initiative. Another big push recently has been Sustainable Development Goals. So within these 17 different goals, you've got a range of different targets. Organisations are looking at integrating some of these different targets within their business. I think this has been a real driver in terms of people not only looking to try and quantify better some of their environmental impacts, but I think people are also starting to get very interested in quantifying some of their social impacts as well, using things like social life cycle assessments to do that. And then finally, you've also got kind of push from investors as well, and from a lot of kind of investor reporting frameworks, things like TCFD, and then of course recently we've had the announcement that the government's aiming to make TCFD disclosure mandatory from 2025. So a range of different kind of drivers that have kind of come about certainly over the last 5 or 6 years in terms of increasing that engagement with actually measuring sustainability. And of course, from an environmental impact side of things, as we're developing new technology and as time kind of goes by in the development process of technology, we're getting sort of environmental lock-in basically from the design stage. So 80% of environmental impact is really locked in at that direct design stage. So if we're going to be measuring sustainability and we're going to be talking about designing new materials, designing new technology, 80% of that impact then is going to get locked in at those very kind of early stages of thinking about that technology. So what's the role of life cycle assessment in all this? So life cycle assessment is a useful method that we can use, which allows us to quantify environmental impact across the life cycle. So looking from raw materials all the way through to end of life. Life cycle assessment breaks down a product into every different part, material and process, and allows us to analyse all the related supply chain components in there. So for every stage, we can look at some of the inputs, so energy, resource and the materials, and outputs, emissions and waste. And we can use this to determine things like total energy demands, resource use, water use, and then environmental impacts like global warming potential, acidification, eutrophication, land use change. We can look at human toxicity, ecotoxicity, a real range of different environmental impacts. And the idea behind this is to stop the problem of shifting kind of environmental burdens from one part of the life cycle to another. With life cycle assessment, we're able to identify environmental hotspots and establish kind of benchmarking potentially against where kind of improvements can then be, future improvements can then be made. It also enables us to understand the true and the sort of total cost of manufacture and design. So that's both from kind of the environmental cost. We can also use life cycle assessment to look at costing. So we can use life cycle costing, or also look at integrating, looking at social aspects as well, so social LCA. So I'm not going to go too much into the framework for life cycle assessments, because I do appreciate this is the evening and you guys have all been at work all day and it is quite dry. But I just give you kind of highlights of the kind of main areas of life cycle assessment. So within life cycle assessment, the first thing that we would start off with is your goal and scope definition. So this is really just looking at defining what it is you're looking at, what is the question you want to ask, and what's the scope of what you're looking at. Here you will also define what your functional unit is, so what is your unit of reference, as well as defining here all of the assumptions that you're making within your assessment. Once you've done that and you've got a real kind of good plan of what you're going to do for your life cycle assessment, then you'd move on to conducting your inventory analysis. So this is where you're collating all of your materials and energy inputs and emissions together. Once you've done that, then you move on to impact assessment. So then all of your information from your inventory analysis is classified and then characterized in your impact assessments to then calculate things like global warming potential or human toxicity, ecotoxicity, those kinds of things. So at each of these stages, you've got a sort of interpretation step. So life cycle assessment tends to be quite iterative. You're constantly kind of reviewing what you're doing as you go through. And there are two different standards which relate to life cycle assessment. So you've got your ISO 14040 and your ISO 14044. So a little bit of sort of history around how life cycle assessment has been used to date. So it sort of started out in the sort of late 1960s. Coca-Cola were one of the first companies to carry out a life cycle assessment. They were looking at contrasting glass bottles with aluminium cans. And it sort of had progressed within kind of companies using life cycle assessment in sort of quite a sort of ad hoc way, really until the 90s, when the first kind of proper frameworks and ISO standards came out to enable us to kind of do LCA in more of a sort of consistent way. Following on from that, life cycle assessment has been continued to be used by businesses. It starts to be used in more of a sort of regulatory and compliance context, and now increasingly is used in a kind of policy context as well. So within the kind of policy side of things, most notably, life cycle assessment is used within the Renewable Energy Directive, and so informing a lot of policy around use of biofuels and bioenergy. I would say that the kind of increased interest in using life cycle assessment in policy and to direct policy decision makings has certainly pushed LCA into kind of a very interesting space, actually. So, we're still using life cycle assessment to understand and do comparative analysis at kind of a process level with two different products. But using life cycle assessment, I think it's very interesting when we're looking at understanding what the potential implication might be of introducing a new technology and kind of trying to understand all of the different aspects around that, integrating things which are a bit more kind of dynamic, trying to think about whether or not there's going to be any kind of rebound effects, or what the socio-economic interactions are going to be. So I think the kind of move into the policy space with LCA has actually kind of made things, I think, very interesting in terms of the types of questions that people are wanting to use LCA now to answer. So I've got an example of an LCA that we've conducted at NCC, because I think sometimes when you're talking about LCA, it's a bit abstract, and kind of it's quite nice to actually see how someone's done an LCA and the types of information that you can get out of it. So this is a project that we carried out looking at placing the rear dead beam in a Ford Transit van. So we were looking at contrasting the current use case, which is a steel beam and steel fittings, with a composite beam and aluminium fittings, and then a composite beam with steel fittings. So the process that we looked at to produce the composite was a pultrusion process. We're looking at glass and carbon fibres and epoxy resin. And you can see that for the different use cases, that the steel beam significantly heavier than the composite beam, so you're getting lightweighting effects there, and then reduction in fuel use during the use phase. So the aim of this was to assess which scenario provides the best performance in terms of carbon footprints, looking at raw materials manufacture and then the use phase of the vehicle. So we had some sort of challenges in doing this around finding data and kind of modelling some aspects from, say, the protrusion process, but also defining some kind of key parameters for the functional unit, and sort of defining a model to look at how we would be able to quantify CO2 savings due to that lightweighting effect in the use phase. So we used secondary data to model the pultrusion process, and secondary data for some of the raw materials as well. We created a process flows out, so we've been using Gabi, which is commercial LCA software, to create this model, and then we looked at a kind of use case of 250,000 kilometres travelled, and calculated global warming potential in terms of kilograms of CO2 equivalents for raw materials manufacture and use phase. So overall, what we found was that the scenario number 2, so if you just looked at raw materials and manufacturing only, scenario number 2, which was the composite dead beam with the aluminium fittings, this had the highest impact in terms of global warming potential. You can see that a lot of that impact is dominated by the actual kind of aluminium mounts and fittings part. But what we found was, when you took that through to the use phase, that both of the composite scenarios, you were able to get a reduction in impact, and sort of a payoff of around 40,000 kilometres from using those two kind of different composite scenarios. So overall, although the scenario 2 had a higher kind of raw materials and manufacturing impact, actually when we take account the use phase as well, the composite performs better than the steel comparator. So just a note with this, obviously we just looked at raw materials manufacture and use. We didn't take into account end of life, and of course that is a big part, particularly of sort of within kind of vehicles, due to kind of end of life vehicles directive. That's kind of an important element when you're looking at a vehicle. So just to guess a bit of a note, so that's something that we didn't take into account with this study. So that's a kind of example of an LCA that we've done at NCC. So thinking about how we apply life cycle assessment now to new technology. So LCA in the kind of new tech space suffers from this idea of the Collingridge dilemma, in the sense that at the early stages you have the most design freedom, but you also have the least knowledge. And as your knowledge increases, your design freedom decreases as the technology diffusion increases. So what that means for LCA, and what the implications of that are, is that at the kind of very low TRL level, so technology readiness level, sort of 1 or 2, where you're looking at sort of a basic kind of concept, you've got the least amount of data and you've got the highest amount of uncertainty. When you go through to TRL sort of 7+, so commercial scale, you've got the most amount of data and the lowest level of uncertainty. But of course, we know that we need to be able to assess new technology. You know, lock-in happens at those very early stages, and so we know we need to be able to do that. But we're sort of tackling this low level of data, very high uncertainty. And we can sort of distill that out into several different areas. So comparability is a really big challenge. So being able to find a functional unit which enables you to show equivalence with incumbent materials. So maybe you've got a material which has, you know, particular properties, aspects in the use phase, where it's quite hard then to compare with other incumbent materials. Maybe you aren't really sure actually how that material is going to be used, what applications that material might have. Then on scale as well, navigating how to evaluate production properly, where at the moment you're just looking at kind of a lab scale process. That might be very different when you scale up. Of course, things like yields might be very different when you scale up. And even looking at LCA at the lab scale and using that to then direct design decisions. Life cycle assessment at lab scale might not necessarily be a true reflection of where exactly the main environmental impacts are going to be. Then you've got this challenge of data, so a real lack of primary data, a reliance on proxy data for different parts of the process as well, and then, you know, how truly representative is that data of the actual process that you're looking at. Uncertainty around, you know, performance at end of life. End of life procedures being very poorly defined as well, really challenging in terms of being able to effectively model that. And then environmental impact methodologies that might not be able to completely represent materials specific impacts. So this is a particular function of nanomaterials and some of the challenges with modelling nano-specific aspects, but it is also a challenge in a number of different areas as well. So, for example, we can't at the moment properly model ocean plastic, for example, and the effect and fate and exposure pathways for ocean plastics and kind of what happens there, and able to sort of capture those aspects in life cycle assessment properly. And then on communication and reporting, so the lack of sort of standardized approaches in dealing with and communicating uncertainty is challenging. Only around about, even when you're looking at across all LCAs, only around about 20% of LCAs do some kind of uncertainty analysis within them. And of course, you know, even when you're looking at a new technology, you want your life cycle assessment to tell you something. You don't just want to do an LCA and sort of not really be able to say anything about the technology you're looking at. So you want to be able to apply and communicate uncertainty, but do it in a way that at least directs some decision making, even if it's to identify and highlight where there are really big data gaps that you need to deal with. And then, you know, being able to select a comparator technology and be able to do that in a way which kind of fairly reflects the development stage of the technology that you're looking at is difficult as well. Because, of course, you know, the technologies you might be comparing it to, they've had years and years of process, efficiency improvements, that, across the product life cycle, being able to develop markets for different co-products and byproducts. So, how do you kind of effectively compare and fairly compare your technology is challenging as well. So, moving on to give an example of a new technology. So nanomaterials used in a range of different consumer products, paints and coatings, textiles, toys, sports equipment, a whole range of areas, food. So very important that we understand what some of the potential impacts are. We're able to characterize some of the nano-specific aspects within products, and certainly relating to human toxicity and potential ecotoxicity in the environment as well. There are some real challenges for applying LCA towards nanomaterials. The absolute kind of big one is that, unlike everything else, toxicity, typically other bulk materials driven by mass, you've got a direct correlation between how much of a substance you have and what your environmental impact is going to be. Nanomaterials toxicity is driven by particle size, and so that immediately creates a real challenge when looking at life cycle assessment, which is calculated based on a mass and energy flow. Another challenge is around representation of some of the kind of nano-specific properties and the performance of nanomaterials in the use phase, very challenging. You've got issues around limited availability of data as well. So very patchy coverage of production data, huge ranges in kind of production data values. Lots of issues around understanding fate, understanding use phase aspects, degradation, things like that as well, and sort of limited data for that, and then linked with that life cycle impact assessment data as well. So currently, the big challenges there are your human toxicity and modelling ecotoxicity, specifically around nano aspects. So we don't have characterization factors which are kind of widely applied to enable us to kind of take some of those nano-specific aspects into account. So those are kind of some real challenges that we have with nanomaterials. So one of the things that I was involved with at National Physical Laboratory was creating some guidance around applying life cycle assessment to engineered nanomaterials, so specifically focusing on manufactured nanomaterials. Of course, we've got nanomaterials which occur through the use phase of certain products. We've got nanomaterials, obviously, which are naturally found in the environment, so specifically focusing on those which are actually manufactured. We looked at applying some guidance, so using the ISO 14044 standard to help people evaluate nanomaterials in a sort of an easier way. So the way we did this was kind of go through the standard. We had 3 different LCA case studies. So we had one on nano silver in textiles. We had a case study on titanium oxide facade coatings, and we also had then one on carbon nanotubes in electronics as well. So we had case study examples of how we've tackled different aspects there. So I've just pulled out one of the figures from the standard, which is just looking at some of the kind of principal causes of variability and uncertainty, and focusing in on some of the ecosystem and human health aspects there. So some of the key areas, say for example, nanoparticle kind of characterization, would be things like data availability. So the kind of key ones are marked there in the longer length in black, kind of the main aspects. So things like data availability, and then you've got some challenges around some sort of exposure assessment, toxicity assessment, and impact assessment there as well. Moving on to talk about composite materials. So of course we use composites in many different things already, but the reason composites are super important, they're going to be more important in the future, is that every technology we can think about, which is going to push us forward to a low carbon economy, that's going to kind of lead us to be net zero by 2050, these all contain composites. So whether or not you're talking about electric vehicles, talking about hydrogen vehicles, electric planes, infrastructure that's going to enable us to deliver hydrogen nationally around the UK, low carbon buildings, wind turbines, increased use of renewables, is all quite composite technology, which is why composites are very important and will increasingly be important in the future, as well as we look towards kind of lightweighting more things. We want more durability, more corrosion resistance, that kind of thing. And of course, one of the challenges is that, you know, as soon as we start reducing operational carbon in buildings, as soon as we start lightweighting vehicles and reducing use phase impacts, which typically tends to be where a lot of the environmental impacts is currently concentrated, we then see a higher proportion of the overall impact being concentrated in the production phase. And of course, composites can have quite a high embodied energy associated with them. Some of the challenges when applying life cycle assessment towards composite materials. So a really big one is data, big data gaps. So not just in some of your kind of emerging or bio-based materials, but even in you know, really digging into kind of pan-carbon fibre as well. Big data ranges and a sort of real lack of transparency as well. So it's quite difficult. A lot of the data that we've got on composites is sort of aggregated industry data, very difficult to dig into and understand kind of where some of the sort of end global warming potential, end energy numbers are kind of coming from. Then there is sort of challenges around representing kind of materials performance and properties in the use phase. So making sure that your functional unit adequately represents the advantages that you can gain from sort of lightweighting or increased durability in the use phase. Understanding the role of bio-based composites, bio-based materials as well. So what is the right mix of bio-based within, you know, all the sectors that we work in with composites? What's the right mix of bio-based, and what is the right bio-based materials to use as well? And then finally, treatment of end of life and kind of making things more circular. So the composite supply chain, very linear at the moment, but also, you know, we need to be able to understand and evaluate end of life. We need to be able to do very robust cradle to grave life cycle assessments of composite materials. And at the moment, you know, we are still kind of developing the technology to deal with composites at end of life and to recycle composite materials. So linked to that, we have got a core program at the moment with our kind of some of our partners at NCC, looking at kind of tackling some of these issues around the composite supply chain being very linear. So one of the ways that we can improve circularity, of course, is recycling. And so this project is looking at the reclamation and reformatting and remanufacture of carbon fibre from a vertical tailplane, and then using that to produce a kind of demonstrator product. So one of the ways in which we're using life cycle assessment within this is that we are integrating life cycle assessment with a techno-economic analysis and a supply chain analysis. So what this really gives is a much broader, holistic perspective, not just looking at environmental impacts, not just kind of evaluating the process as is, but really asking how viable commercially is this particular technology, and is the supply chain that sits around, or potential for a robust supply chain that sits around carbon fibre recycling going to be in the UK. So this is a project that has just kind of started, and I'm really hoping that we're going to be able to present on this during the IOM3 kind of sustainability week in September, once we have got some interesting results, hopefully, from this. So finally, moving on to managing uncertainty and looking at some of the ways we can do that. So there's loads of different ways in which you can look at talk about categorizing and visualizing uncertainty, both specific to LCA and also generally when we're talking about modeling. One of the most kind of useful ways I've always found of thinking about this is using this kind of location, nature and level framework of looking at uncertainty. So identifying the location of the uncertainty, where is that found within the model? So is that relating to the context within what you're looking at? So your choice of system boundary, is it related to the nature? So is it uncertainty which is due to a lack of knowledge or an imperfection of knowledge? So that being your kind of epistemic uncertainty, or is it an inherent variability, so aleatory uncertainty, something that's always going to be there? And then finally, kind of thinking about the level of uncertainty. And I think level is really important here when we're thinking about how then we tackle how to handle that uncertainty. So, we are on a spectrum of understanding of knowledge about certain things. And so at one end of the spectrum would be your kind of deterministic knowledge, where you're able to actually define different statistical ranges for particular numbers, all the way through to total ignorance, where we don't even know what we don't know about a particular thing. So it's really important to, I think, understand where you are on that with regards to some of the different aspects of uncertainty, because I think that really directs them what you're able to do about it. And there are different things that we can use in life cycle assessment to manage and communicate uncertainty. It's probably one of the most well-used methods is Monte Carlo analysis, so probabilistic simulation. There are other types of analysis that you can do related to Monte Carlo analysis. So whether or not it's sort of Taylor series or fuzzy sets, but the most kind of commonly used probabilistic simulation being, or most commonly used way of propagating uncertainty being Monte Carlo analysis. You've got other types of analysis that we can do, so things like scenario analysis. So you've got your base case, and then defining a range of different variations of that base case to understand what different scenarios might look at. You can then also look at sensitivity analysis, and this can be done either as a kind of one at a time sensitivity. So you change a particular parameter and then you run your model and you look at what the effects of that change has been compared to your base case, and you might change something else and then see what the effect is. Another really kind of interesting way of using sensitivity analysis is performing a global sensitivity analysis. So that's taking all of the different variation and ranges in your inputs, and then looking at your output and understanding what it is within your output range, what uncertainty from your inputs most contributes to that then output result. So by doing a global sensitivity analysis, you can kind of hone in on like what are your most problematic inputs in terms of uncertainty kind of distribution. So, I mean, this is by no means an exhaustive list of the different types of methods for evaluating and kind of communicating uncertainty in LCA. We've got other kind of more qualitative means, so expert review and things like that. You've also got pedigree matrices. So these are used to enable you to determine quantitative sustainability, quantitative values based on qualitative evaluation of uncertainty across a range of different areas. But these are kind of, I guess, Monte Carlo analysis and then scenario and sensitivity analysis, probably the most commonly used ways of evaluating and communicating uncertainty. So another method that we can use is screening or decision frameworks, or combining LCA with different tools. So this is used very commonly when we're looking at life cycle assessment of nanomaterials. So there have been lots of frameworks suggested that use risk assessment alongside life cycle assessment to fill in some of those gaps that we currently have around human health and an ecosystem impact from an LCA perspective. So trying to understand a little bit more about kind of fate and effect modelling for the risk assessment side, and use that alongside life cycle assessment. And we can even apply more of a screening kind of life cycle thinking approach, where we might not have all the data to do a kind of full LCA. We can also combine this with other sustainability metrics as well. So one of the kind of increasing things which is being used alongside LCA is techno-economic analysis as well. So this will give you an idea of, not just some of the environmental impacts, but also the economic viability of a particular technology as well. Understanding, what aspects within that technology needs to change in order for the technology to become more economically viable, or what are the trade-offs between environmental aspects and environmental decisions that you might make in terms of designing that technology from an environmental perspective versus an economic perspective as well. And there's other metrics that you can use, whether or not it's trying to, depending on some of the questions that you might be trying to ask. So, different types of socioeconomic metrics. You might want to combine life cycle assessment with some kind of dynamic modelling, agent-based modelling, to understand how kind of uptake of a technology might work. So there's loads of different things that you can do, just to kind of maybe fill in gaps in the sort of sense in terms of life cycle assessment, and combine that with risk assessment, but also kind of doing a more kind of holistic, wider assessment of a technology as well, that might give you a kind of fuller view of that technology. So what are some of the kind of future steps that are needed? So we need to, big issue with new tech is around data and databases, and we need to be able to have access to data, but not just any old data. We need it to have information around uncertainty, and we need to have the details of assumptions, collection methods. We need to have information about where that data comes from in a sort of a transparent way, in order for us to kind of fully understand that data and the different aspects relating to that data. But that's really important because that's something that's really challenging, and that cuts across all new technology, and whether or not you're looking at kind of nanomaterial production through to composites. Being able to have access to data, and not just any old data, but good data, is really important. And then, what more widespread use of uncertainty analysis. It's something which is increasing certainly in academic space, but I think we need to be using it more on the kind of industrial research end of things as well. And for us at NCC, one of the biggest challenges we've always had to date, I think, is much of our LCA work is very focused on looking at sort of a process-based comparison between a composite product and, say, a steel product. And I think we want to be able to create more case studies where we're looking at being able to dig into data more, be able to show uncertainty, and be able to show the power of what some of the different analysis tools can do, advanced life cycle assessment methods using things like Python, for example, being able to show kind of what capability there is in terms of assessing uncertainty in a way which is still helpful for decision making. And also being able to kind of integrate life cycle assessment with other tools is a very important way of being able to kind of bridge some of those gaps in understanding at early stages of technology implementation. So kind of my key points, so I'm drawing to a close with this. So thanks everyone for still kind of listing on. So application of LCA really, is still growing. It's growing hugely, and of course, a big area of interest, is life cycle assessment of emerging technology, as we're getting kind of push forward for new technology, which is going to enable us to get to net zero by 2050. But one of the huge challenges with applying life cycle assessment to new technology is this Collingridge dilemma, is the idea that change is hard once a technology has been commercialised, but we don't know very much about impacts, or it can't be easily predicted until technology has been more widely developed. So within that, uncertainty analysis is really crucial, with the need to kind of better develop approaches to communicate this for decision making, and certainly sort of standardise the way in which we approach uncertainty assessment also. So I will finish for all of the students listening as well. I will say, well, I hope I haven't put you off life cycle assessment, but I will say, it is a really growing area. I've been contacted by recruiters pretty much every single day this week who are looking for, do I know anyone who has LCA expertise? It's through the roof in terms of the amount of people who are trying to find LCA practitioners at the moment, just because of their increased interest in LCA. Life cycle assessment, I know a lot of people think that LCA people just get a bill of materials and kind of put that information into a commercial LCA software and then get a nice graph at the end. But there's actually so much more to it. If you're interested in going down kind of the more engineering route and looking at life cycle assessment and getting involved more in the kind of process modelling aspects, but also there's lots of potential applications in terms of more of the impact assessment side, and the kind of link with environmental modelling, a link with risk assessment as well. And of course, there's loads of different interesting challenges depending on what type of LCA you're looking at in whatever sector. So I think there's loads of interesting opportunity in the LCA space. So yeah, so I hope I haven't put any of you off thinking about LCF is something you're interested in the future. So I will finish there because I think I've been talking on for almost an hour now. But yeah, so thank you very much for listening. Any other questions that you think about, or if you want to talk to me separately, then I've got my email address at the bottom there. Do drop me an email. Always kind of really happy to hear from people. So yeah, any questions that you think about kind of after this event, don't hesitate to get in contact. But I will stop sharing now. And I guess if anyone's got any